So first thing is, as always, you can have a cheat sheet, one side of an 8.5 by 11 sheet of paper. Whatever you want to put on it is fine. The exam will be roughly equally split between the three chapters, 6, 8, and 9. I will probably lean heavier towards 6 and 8 because we are really having to cram 9 in, and it's not giving you a lot of time to really absorb it as much as the first two, so I understand that and will tend to lean a little bit more towards the first two. And for chapter 9, if there's stuff that we have not covered yet, so we have a little bit more left, I'll talk about it when I get there in more detail, but I will not emphasize some of that stuff as much. But that's the main logistics stuff. The structure will be similar. It'll sort of be this ongoing story style thing, but each question is roughly independent of the other questions, meaning you don't need to know the answer to one to solve another. And I'm just going to start recapping each chapter real fast, and then again, because we're sort of cramming things, I will go into a little bit more specifics on what I'll be looking for the exam, just to try and make it a little bit more fair. So, chapter 6, we introduced the idea of energy, essentially because it's just a convenient way to look at things. So, it's this number that when we compute it, we find out by the end of the chapter, it is a conserved quantity. It's this thing that we find tends to be the same before and after different events happen in the real world. We specifically look at just a couple types of energy in this chapter, but you can extend that idea to all sorts, and you essentially give life to the idea of energy just because of how useful it is. It was a man-made idea, but by the end, we use it so much, we treat it with so much respect because of that idea of conservation of it, that it became a way of understanding nature. Anyway, work is the way in which it's transferred, and it is through a force acting through a displacement, meaning through however the object's moving. Work can be positive, negative, or zero. It doesn't have a direction, it's just a number. Positive means the force is acting in the direction of the displacement, the direction the object moves. Negative work means that it is opposite that direction. Zero work means that it is perpendicular to that direction. We can then start putting together the work done by multiple different kinds of forces to talk about net work. The sign of that tells you whether something will speed up, slow down, or not change its speed. If it's positive net work, then the object will speed up. If it is negative net work, the object will slow down. If it is zero net work, the object won't do either. It will stay at the same speed. And that is the statement being made by the work energy theorem, which is this thing down here, that the network, which you can think of as look at all the deposits and withdrawals happening in your checking account, that is going to determine how the checking account value changes. But if we look a little bit more carefully at some of those forces and the work they're doing, we find that some of them aren't really taking that energy out of kinetic just to throw it away to somewhere else, to someone else's account. Really, they stay with the system you're looking at, but they just don't stay with the speed of it, with the kinetic energy. They're actually taking it into a different type of energy, the potential energy. And specifically gravity, there's a gravitational potential energy. And it's the idea that when, say, you throw a ball up in the air, the ball is going to lose kinetic. It's going to slow down, but it doesn't lose it forever. For some reason, when the ball falls back down towards your hand, it gains all that kinetic energy back. And that's the sense in which we think of that energy must have been held on to so that it could be given back. And we use that to invent the idea of potential energy. We say, when something is rising, gravity is pulling downward on it. And so it's trying to extract that kinetic energy away from it. It's doing negative work on it. But at the same time, we think of that as some kind of something is building up, something's being stored up, that potential energy. And so we get this relationship between between the work being done by gravity and potential energy. When the work done is negative to slow something down, potential energy is increasing because you're doing that work to put energy into that potential energy account. When the work done by gravity is positive, that's giving the energy back to kinetic. And again, that's going to reduce the potential energy, how much is in that account. So we think of gravity as a conservative force because it holds on to the energy. That's kind of the most intuitive definition of a conservative force. A non-conservative force is something like friction, where it really doesn't hold on to it. It's not planning to give it back at a later time. It's transferring it to some other part of the system or somewhere else entirely. That lets us make a distinction in the work energy theorem between conservative and non-conservative forces. If only conservative forces, so things like gravity, or in chapter 10, we'll briefly talk about springs, if things like that are all that's acting, all that's doing work on the system, then you don't really ever lose any energy. It just gets passed between kinetic and potential. So it doesn't exit the system, it's just held within a different part of it. And that's the idea of conservation of energy, specifically mechanical energy, which is kinetic plus potential. If there's nothing like friction to take that energy, to take your money away, or something like someone pushing to give energy to the system, to give you money, then the most that can happen is your money is just transferring back and forth between your own two accounts, your kinetic or your checking account and your potential or your savings account. And that's a really useful concept because it lets us connect two different kind of states of the system, for instance, something's at the top of a hill versus the bottom of a hill, without really worrying about the details of what happened in between. You don't need to know all about the slopes and all that like you did for Newton's laws. You just do this sort of balance sheet to say, well, my initial budget of energy was 300,000 joules. How did I get that? Somehow work was done to get that thing up the hill, but we're not concerned about that from here on out. All I know is I better keep that same amount as long as things like friction aren't taking it. And so if I start with zero kinetic energy, that must all be in the potential energy account. It's sheerly because of the height the sled is at. But by the time the sled gets to the bottom of the hill, it's used up all that potential energy. And again, provided things like friction weren't present, because they really could actually sap away potential energy and not give it back, provided stuff like that's not happening, where must that energy be? In the kinetic account. And that kinetic energy is related to the speed. In other words, with this idea of conservation of energy, without knowing much at all about a system, you can predict the speed of things within it relatively easily. And that's like a huge leap compared to how we would go about it using Newton's laws and then using kinematics. So conceptually, it's just a much more nice way to look at things, is just a balancing act of different types of energy and how it's being exchanged around within a system. I'll get more into exactly how you need to look at that for the exam once I get through all three chapters. But if we do have things like friction present, it's a non-conservative force. It is doing work. It's sapping away that energy. If I came back up here to this picture, it might be something like, I started with 300,000 joules of mechanical energy, but when I measure my speed at the bottom of the hill, it might only amount to 200,000 joules worth of kinetic energy. And if I look at the potential, it's still at zero. In other words, I really did lose 100,000 joules of energy from this system. That's what friction does. It lowers your overall account balance. But we still have a way of dealing with that. That's the work energy theorem. That's the most general statement made in the chapter. Conservation of energy is a special case of work energy. Power is not going to be on there because it's sort of an afterthought at the tail end. And again, this whole recorded long example is up on Canvas as well, and it's a good one to look at for the kinds of calculations that show up on the exam. All right, chapter 8 is much more straightforward because it's really rehashing a lot of things that have already been said about motion, but now for rotational motion. So instead of regular displacement that you moved from here to there, you have angular displacement. You rotated from here to there. The sign convention is probably backwards to what should feel right, but this is what we go with. Clockwise is actually negative rotation, counterclockwise is positive. And the angle is a more convenient way to talk about things that are rotating, because if we looked at specific points on a rotating object and we were just really stubborn and said, you know, I really want to talk in terms of distance and like actual displacement in meters. The problem is that depending on the circle that each of those points ends up moving through, they're going to travel totally different distances. And so you have to account for a different number for every single point on this guy's body. Or the alternative is all those points can agree on the angle they rotated through. It will be one number describing every single point on him. That's why we pivot to angular variables, is they're more convenient to use for rotating things. But if we do ever want to go back to the translational motion or the meters instead of degrees kinds of motion, the link between the two is the radius at which the object is rotating. So this is the distance an object travels, the arc length it moves through while something's rotating. This is the angle it rotated through, and the connecting variable is the radius. And we'll see that several times throughout the chapter. That equation does only work if your angle is in radians, because that equation is actually what defines what a radian is. It's the angle taken up by the radius of the circle if you try and lay it out over the circle. We continue developing very similar to how we did all the way back in chapter 2, but now in terms of angular things. So if I want to know how fast something is spinning, I talk about angular velocity. Measure the angle it rotates through and the time it took to do that. Divide those, that gives you a rate of rotation. If you want to know in more detail about that rate, maybe the rate is changing because something's going to be spinning faster in just a second or spinning slower in just a second, then you're going to need to think about much shorter time spans to get an accurate description of the rotation, and that's the instantaneous angular velocity. In terms of calculation, we don't really make a big distinction, but that's the conceptual distinction. So, for a changing angular velocity, you're going to need to think about how quickly is it changing? Is it happening to where it starts at one angular speed, maybe it's 1 revolution per second, and it takes a really long time to get up to 10 revolutions per second, it spins up slow? Or does it go from 1 revolution per second to 10 revolutions per second in a half second? It's a really quick spin up. That's angular acceleration. And it's how much did the angular velocity change? How long did it take for that change to happen? Instantaneous, similar idea here of it could be sometimes it's changing really quickly, sometimes it's changing much slower, and so if you want an accurate description, you really got to think about short time spans. The first guaranteed calculation that just always shows up in this chapter is kinematics. Luckily, it's the exact same procedure as for regular old kinematics. You fill in what you're given from the problem statement, and then you use that to pick a kinematic equation. I'm going to say, because I think it's just a fight or flight thing on exams of not really using sort of the structure that we use in class for some of these. Like for exam 2, I saw a lot of just absence of tables, and every time we did a problem with free body diagrams and forces, we made that table to find the components. And it's not that it has to be that way. I don't hate if someone doesn't do it that way, if they have a different way that works for them better. What I don't always understand is if you have no idea, you try and improvise and intuit an answer. But the whole point of structures like this is they're taking some of that load off of your brain so that you don't have to intuit through everything. You have a procedure you can follow and just fill it in, and it sort of throws the answer at you, or at least gets you closer to it. And then maybe you have to start thinking once you get to the solving part, but it's a little less to have to think about. So that's why we have these kind of structures for solving different problems, is not to force you into a box and how you solve it, but to help get you the first 20% of the way, and then it doesn't feel as bad to do the last 80%. So anyway, kinematic problems like that. And then this last little bit of the chapter is that thing we started talking about at the beginning of how you can link angular variables and then regular old linear variables. You can do that for everything, not just the distance something travels, but also how fast is it going. You could talk in terms of how fast it is rotating. That's omega, angular velocity. But maybe you actually want to know, well, how fast is it moving? How many meters per second is it covering? If I strapped a speedometer to it, what would it say? That's tangential speed. And again, The variable that connects them is the radius. How far are you from the axis? If you're really far away and you're going along a circle, you got a much larger distance to cover in the same amount of time as points much closer to the center. So it stands to reason you're going to have to go much faster to keep up. Similar with acceleration. You could be talking about, well, something spinning faster and faster, or going around a turn faster and faster, more angle covered per second. That's the angular acceleration. But instead you could say, well, I want to know how quickly my speedometer reading is changing. Is it going from 0 to 50 within 1 second? Is it doing it within 10 seconds? That's tangential acceleration. But again, they are linked by how far you are from the axis of rotation. The thing that kind of helps understand the difference between them is alpha is going to be the same no matter which part of a rotating object you're talking about. That's easier to see on like the fan blades. Whether you look at a point close to the axis or far away, if you pull the chain on the fan so that it's going to be spinning faster and faster to get up to like real high speed, each of these points has got to cover an additional number of revolutions per second. Maybe turning it on to the high speed is like an extra revolution per second. Each of them has to do that extra revolution per second. There's no difference between them in terms of the extra angle they have to cover. But this guy on the outside, in order to do that, he's going to have to speed up more dramatically than this one right here in terms of if you had a speedometer on that part of the fan, if it was reading 2 meters per second before, while this one was only reading 1 meter per second, when you double the speed, this one might go to 2 meters per second, but this one goes to 4. So it's a 2 meter per second increase versus a 1 meters per second increase for this guy. The last one that is easy to forget about is just you're purely rotating in the first place. So angular acceleration has something to say about are you going faster as you spin, but centripetal is just are you spinning at all? It's going to be present if something is spinning. And it's the thing that keeps the object spinning in a circle. It's what forces you to stay on that circle instead of going in a straight line like you would like to do. The total acceleration is just putting both pieces together. The part about that you are turning and the part about are you doing that faster or slower? Are you going to be turning faster in a minute or slower? And again, we've got this long problem that sort of puts all that together. I was editing that just a little bit ago, and then some stuff came up, but that will be up later. And then chapter 9. So chapter 8 was about qualitative features of something's motion. How fast is it going? How far is it rotated? Is it speeding up in a short span of time or over a long time? This chapter is about why it might do that. So what makes it spin faster or slower, and what resists that? The thing that makes something rotate faster or slower is a net torque, which means consider all the torques acting on an object, add them up, similar to how you do with forces, and that's what determines how something will rotate. So what is torque? It's loosely like force. It's almost the same thing, but now it's not about how it can speed something up or slow it down. It's about how can it turn it. How effective is the force at turning an object? And we found that it depends not only on how hard you push, but it also depends where you push. So are you pushing far away from the axis? If so, you'll probably be more successful. If you're pushing right at the hinge, you won't be. And then it depends on the orientation of the force. If you are pushing perpendicular to the door, so like the blue force, that'll probably go okay. If you're trying to push or pull along the door, that's not going to do anything to turn or rotate the door. You're not going to be able to open it very easily that way. So torque encapsulates all of those things into one quantity. Then we looked at center of gravity, which is just how do we deal with finding the torque produced by your own body weight? Because gravity is pulling on every single part of your body all at once. It's not one singular point, and so there's not a clear-cut distance like we have for this force applied to a door. We got lots of forces that are combining to add up to your overall body weight and to make you tip over if you lean too far forward. So how do you deal with that? Well, you come up with the idea of, is there an equivalent point? Like, could we pretend all of your weight is actually only at one singular point? And if so, where would that point be? Well, there turns out to be a spot like that. It's called your center of gravity. And we can use it and get the exact same amount of torque as we would get if we really did account for every little point on your body being pulled on separately. For simple objects, it's just this weighted sum of where their weight acts, so their individual centers of gravity. But for more complicated things, we just aren't going to worry about it in here. It's calculus and it's not pretty, but it's the same idea of you can pretend there is a point at which the entire weight of your body is pulling you from. Then we found that equilibrium actually means more than just not changing how it's moving, so not speeding up, slowing down, changing direction, but also not changing how it's rotating, so not rotating faster or slower, or changing the axis of rotation, but we don't talk so much about that one. As far as exam type questions are concerned, it's really mostly like the part we actually did do for this. So just all the torques have to balance out if the object in question is in balance. So in the review thing, there's something more like a seesaw. That kind of problem is pretty common. It's just a question of how do you make it so you balance the seesaw if you've got one person sitting further away from the axis and one person sitting closer. And in that case, it's not just their weight that's important, but where is that weight? So like call that x1, that's his weight, and then this guy is at x2, that's his weight. What actually has to happen in order for the seesaw to balance is that the torque balances. So the guy on the left is going to cause a counterclockwise or positive torque. The guy on the right is going to cause a clockwise or negative torque, and we need those to add up to 0 for the seesaw to not tip. So we could talk in terms of those individual torques. Guy on the left, it'll be his weight times the distance he is from the axis, and then times sine of the angle between those, but that's going to be 90 degrees. And then similar for the guy on the right. And so it might be a question like, how far does the guy on the right have to stand to make sure the seesaw balances? Well, you can just solve that. It's W1x1 over W2. But in general, you can see even for this more complicated problem we talked about in class, it's the same idea of just balancing of torques. What if torque doesn't balance? What if you do have a net torque? In that case, we're not dealing with equilibrium, but we're dealing with the second law. It says what happens in that case. You get an angular acceleration, which means something will spin faster or slower than it was before. So up here, it might be, say this guy was just so heavy, there's really nowhere the guy on the right can stand to bounce the torque he produces. In that case, the seesaw will start to tip towards the left side. The angular acceleration, how quickly it is turning from one moment to the next, how that's going to be changing, is determined from this. It's the second law, but for rotation. It depends on not only the net torque, so that overall adding up of each individual torque, but also what it is you're trying to turn, and that's described by the rotational inertia. So that would be that you are trying to rotate this seesaw. In addition to, you would consider these guys as like point masses. They're a mass that's concentrated here and then concentrated here. And you could add up all those rotational inertias to get that. That's a little bit more in the weeds than we'd probably see on the exam, but that's the idea. And that's what these formulas are telling you for different shapes. If you're trying to spin a door this way, it will resist in that amount. It will depend on its mass, how wide it is, and then this extra factor out front. And that's what we started talking about with this race here. And then this problem is going to be the last one that's like a calculation type problem that you could see. We'll cover that on Tuesday. Since we have not gotten to it yet, I'll just say we won't worry about angular momentum as far as the exam is concerned. We're still going to cover it, but as far as the exam goes, it's just squeezing too much in, so we'll cut it. But
it will be on the final.
It's possible. I'll be honest, when I have asked the question, kind of question I usually ask for angular momentum, it's the one that everyone gets right because there's a demo for this that I really like, and it kind of makes it really clear. So I hope it's not like a hard question. But anyway, yes, it could show up on the final. This last piece is just sort of your dictionary to translate from talking about regular old motion, straight line motion, to rotation. And I could say for position, sometimes we say arc length, so S instead. So that's sort of a recap of the concepts of each chapter. Now let me get to, well, what kind of questions do I like to ask for exams? So for chapter 6, the signs of the work being done by different forces. So you may have some scenario you're given, like a guy's pushing on something. Maybe it has wheels on it, I don't know. There's lots of forces on that thing. There's a normal force. It has some weight to it. He's pushing on it. I'll just call that F. There's some friction. So the question is just what kind of work is each force doing? And you'd say, well, him pushing, it's positive work, it's trying to speed the object up, assuming we are moving this object to the right, because it's in the same direction as that. Friction's trying to slow it down is negative work. Normal force is not doing anything to speed it up or slow it down. It's zero work. And then the weight is doing zero work because, again, we're moving perpendicular to the pull of gravity here. If this cart fell down some stairs, gravity is definitely going to be doing some work. But this is along a flat surface where you don't expect gravity to speed it up or slow it down. So that can be more like a conceptual question, like a no work required type question. Calculation is using work energy theorem. So actually find the work done by all these individual forces and then tell me what is the final speed of the object after all that work has been done. So the net work is just add up the work done by all the forces that are actually present in the problem. The right-hand side, change in kinetic energy, which final minus initial. So it just comes down to if it starts from rest, this is zero, but it could be it started from some other speed. To find the final speed, you're just going to have to solve for v final. Questions like that are pretty common, or some variant where you're solving for something else in that expression. The next conceptual type thing is, can you tell if mechanical energy is being conserved in some scenario? So when is mechanical energy conserved? What are the conditions for that? Can you tell if it is being conserved or not? And in a problem where it is, can you apply it? And applying it means an initial kinetic energy plus initial potential equals final kinetic plus final potential if energy is conserved. And you'd be given the height something started at, the height it ended up at, and its initial speed. Tell me the final speed. Or you're given the speeds and I want to know about a height. It's just given some of the things, find one of the others, but using that expression. That's the big stuff I can think of for chapter 6. I guess I should say, just because it's not on here, on this list I'm making right now, does not mean I can't ask about it. But these are things that I ask about like every time I write an exam for these chapters. For chapter 8, it is kinematics, meaning where you have to do your little table. And then given 3 things, find a fourth. A sort of subcategory of that that just can mess people up when doing these problems is knowing about signs. So again, clockwise is negative, counterclockwise is positive. And I can be sneaky. I can say there is some angular velocity uh, of magnitude such and such number, and I won't tell you the sign, but I'll say like very, casually, it's rotating clockwise. And that'll mean you should have put a negative into your table right here. It's negative whatever number I said. But if you don't know the sign conventions, you won't get that. And that can actually give you a wrong answer if you don't incorporate that. Similar for accelerations. So it's that thing we said about same or opposite sign. So similar thing here. I could give you a number, but I'm more sneaky about telling you whether it should be positive or negative. I won't outright say it all the time. I'll say this object is going to be uh, spinning faster here in just a second. And maybe I did tell you about the angular velocity. Maybe you did know that's negative. But you're going to have to infer from the fact that the object's spinning faster and faster that the acceleration should also be negative, should have the same sign. I won't outright always say it. That's the big calculation. The other one is linear versus angular variables. So the linear variables are the arc length, the tangential speed, tangential acceleration. The angular are angular displacement, angular velocity or angular speed, and angular acceleration. And it might be a question where you know something on the right-hand side, and I ask, well, how far has it moved? That's the arc length that's traveled through. It's r times that angular displacement. Or how fast is it going in meters per second? That's r times the angular velocity. Or what is its acceleration in meters per second? That's r alpha. The other piece conceptually to know about these is these will be the same for every point on a spinning object. Like the bike wheel that we kept bringing up. Every point on it has to rotate through the same angle when I spin it. Every point on it has to be rotating through the same angle per second. So the angular speed has to be the same for each point. And if I spin it faster and faster, every point on it is going to have to speed up by that much as far as what angle it's covering per second. But the left-hand side stuff, those can be totally different because of this radius thing. If you are further away from the axis of rotation, it's going to be harder for you. You're going to have to cover more distance, while the points close to the axis don't have to. You're going to have to go faster than the points near the axis in terms of meters per second. And if the wheel starts spinning faster, you've got to speed up even more than the points closer to the axis just to keep up with them, because it's this larger distance, this larger circle you're having to move around. So these can be different for different points. And then the last thing is the types of acceleration. What is the distinction between them? And when do you have them? When don't you? So we've really got, it's really three main types. So angular, tangential, and centripetal. It's just you put some of those together into the total acceleration. So it's more knowing the distinction between these three things. Again, angular is, are you rotating faster or slower? So if something's spinning at a steady rate, it is not undergoing an angular acceleration. It has zero if that's the case. But if it's going to be spinning faster and faster and faster, that's an angular acceleration. If it's going to slow down its rate of spin, that's angular. Tangential is about something is moving faster or slower in the sense of the meters per second reading, the speedometer reading, is changing. So that corresponds or goes with the angular acceleration of, if, for instance, I have my spinning wheel. If I give it a big hard spin, every point on it is going to be rotating faster and faster. That's angular acceleration. But also, every point on it is going to have to cover more distance per second. That's a tangential acceleration. Centripetal is just, is it rotating, period. If it is, it has a centripetal acceleration. So the only time when we're talking about rotating objects that you wouldn't have a centripetal acceleration is if it wasn't moving at first and you've just started spinning it up. So at that initial moment before it's actually spinning, so you gave it a push but it's not spinning just yet, that's the one moment for a rotating object that it doesn't have a centripetal acceleration, and that's covered in that long synthesis problem. Total acceleration is just put together the part about that you're turning and the part about that you're speeding up or slowing down. I think that's the main stuff for 8. For 9, finding net torque. So you've got multiple forces acting on something. Can you tell me the overall torque acting? And to do that, again, you've got to worry about if it's going to make something spin clockwise, that is a negative torque. If it's going to make it spin counterclockwise, that's a positive torque. Other than that, addition is just adding. It's not vector stuff where you have to worry about components. You just add all the numbers you get. And for each individual torque, you account for the sign, so that plus or minus, depending on which way it's going to cause rotation, force, sine theta, and then how far that force is being applied from the axis. The other calculation thing is finding an angular acceleration if you know the net torque. So I give that door a hard push, and I can find the torque I'm exerting on that door. But can I figure out how it's going to rotate as a result of it? That doesn't just depend on how hard I'm pushing, the torque I'm producing, but the door itself is going to resist that rotation to some degree. It has some rotational inertia. And that would be the thing where you just have to go to the front page and say, well, what kind of shape is this? If it's a door, that's that rectangle about one end. And the equation sheet has a specific expression for the rotational inertia of that. And that's what has to go here. That's what you would have to calculate. Conceptually for this chapter, well, since I'm cutting off the stuff about angular momentum, that's a lot of what I like to ask for concept questions for this chapter. I guess that's the main thing because the chapter really doesn't have a lot going on in it. Like if you just kind of step back and look at what's covered in it.
It feels like there's a lot going on.
It does when we're in the thick of it, but hopefully, I mean, even these recaps of like what we actually covered, it's just so many words have to be said to introduce the ideas, but once they're introduced, it's much easier to talk over them. Center of gravity, maybe, is the only thing about conceptual of like, can you tell when something will have a lower or higher center of gravity? And that's just going to be where is more weight concentrated in the object. If you've got a heavier end to it, you're expecting the center of gravity to be more towards that side. And that's more what's going to cause the tipping of the object in the first place. I think that is the main kind of things. Questions?
I don't really have anything like specific, but I just know the quiz question about the different types of acceleration was like definitely confused me. Like an object is rotating and it speeds up,
Mm-hmm.
and then it asked basically if it was centripetal or tangential or angular acceleration. And I understand it now, kind of, but
Okay.
I think I
Yeah,
got it
so
wrong.
so centripetal is the part it's purely spinning. So it's really just down to angular or tangential. So that's the first
Mm-hmm.
thing is just faster or slower, centripetal doesn't care. It's purely just that something's spinning. What does is tangential or angular, and they care in slightly different ways. Angular cares that the angle being covered per second is growing or getting
Mm-hmm.
smaller. Tangential cares that the meters per second, the actual speedometer reading, is getting bigger or smaller. So I'd have to remember how I phrased the question to say what the right answer is for it, but it's trying to focus on, well, is it talking about that the angle that is rotating through each second is growing, or is it talking about the
Mm-hmm.
distance?
Yeah, I don't remember how it was phrased. I think, but it was one of the two, and I think I put centripetal because I didn't remember that it was only about the direction. Like it was only about that it's rotating, it didn't speed up.
Okay.
So,
Okay. Yeah. So that is the distinction. I think the best example I can give of this is, and maybe a more everyday one, is when you first turn on a dryer and it starts tumbling the clothes. The moment you turn on the dryer, it has no centripetal acceleration because it's not turning yet. But it does have a angular acceleration because it's gonna be turning pretty soon, meaning it's gonna change its rate of rotation from 0 to some non-zero value. If you look at any clothing item within the dryer, it's also going to have tangential acceleration. It's going to cover some additional distance per second. It's going to pick up some speed. Or you could look at points on the actual drum of the dryer and say the same thing. Each of them will be moving faster, more meters per second in just a little bit. Once you reach the steady speed of the dryer, like it's entered that tumble dry kind of steady cycle, it has centripetal acceleration because it's spinning, but it has no angular acceleration because it is not going to be spinning any faster anymore. And then
Okay.
tangential, same sort of deal, although the clothes, since they're not stuck to the side, I mean, they can be doing all sorts of things. To actually describe that would be worse. But say you're talking about like a sock stuck to the side of the dryer, that you can say it will not have a tangential acceleration once the dryer stabilizes out because it's not going to be moving any faster in just a second. It's going to maintain its speed as it moves.
So if something has an angular acceleration, then it has to have a tangential
Yes.
acceleration.
Yeah, and they always go hand in hand because of, or I should circle this one, because of that radius thing connecting them. The only, and this is like a special case, I don't want to hurt your brain more, but
Oh,
if the radius is 0, then technically it can have an angular acceleration but no tangential acceleration. So that's going to mean, imagine I'm standing at the North Pole of the Earth. If the Earth
mhm.
started spinning faster, I would still spin faster with it, but I'm not moving any faster because if I'm at one of the poles, I'm not moving, period. Like,
Oh yeah.
yeah, like I'm just standing here and rotating with the Earth, but I would only be moving if I were somewhere over here so that I'm going around a circle with the Earth. So
Okay.
that's another, it's a nitpick and not one that I would ask about, but it is something.